Alrighty, let's do another one that's even more complicated because now the upper limit of this integral function is no longer x. No, look at it. It's x cubed. Oh my gosh, I feel like a composite function is coming here. Here's the deal. We're asked to find the derivative of the integral from the lower limit 0 to the upper limit x cubed of sine of t squared dt. Solution. Well, here we have g of x is equal to the integral from 0 to x cubed sine of t squared dt. And you know the fundamental theorem, part 1, says that if little f, the interior function, the integrand, sine t squared in this case, is continuous on the interval from a to b, that means that the derivative with respect to x of g of x, which is the derivative with respect to x of our integral, which is normally just a to x f of t dt, equals f of x for all x on the interval from a to b. All right, now, you know, it's a little bit misleading to say that this is exactly the same as the fundamental theorem because it's not x at the top of that integral. To find the derivative with respect to x of our integral from 0 to x cubed of sine t squared dt, we first have to let u, the upper limit, equal x cubed. And look, we need to recognize that sine t squared is the little f of t in this problem. The little f of t. Okay, so we've got u equals x cubed. Well, that means that du dx, the derivative with respect to x of u, is equal to 3x squared. Then that means that now we're looking to take the derivative of a composite function. Okay, let's see if you guys can wrap your brains around this one. It is a composite function. It's not g of x we're taking the derivative of. We're taking the derivative of g of u. In other words, g of x squared. Wow. Okay, hang on. Here we go. So what I was previously calling the derivative with respect to x of g of, quote, x, g of x, well, in the fundamental theorem, it calls it g of x. But here we don't have the integral from 0 to x. We have the integral from 0 to x cubed. So this is actually a derivative with respect to x of g of x cubed, because g of x would only equal the integral from 0 to x. And we have the integral from 0 to x cubed. So we're taking the derivative of g of x cubed. All right, so that's equal to the derivative with respect to x of g of u. Okay, that means we're taking a derivative of a composite function because u is a function of x. So we're going to apply the chain rule. First, we have that it's equal to f of u times, we hit it with u prime. Now, why is it f of u? Because the fundamental theorem part 1 says it's f of u. And then why are we multiplying by u prime? Because the chain rule says we have to do that. F of u is a composite function, or I should say g of u is a composite function. So when we take the derivative, we have to hit it with u prime. All right, what's f of u? Well, let's see. F of t was equal to sine of t squared, so f of u is equal to the sine of u squared. Okay, I'll replace f of u with sine of u squared times u prime. What's u prime? Well, because u is equal to x cubed, that implies that u prime is equal to 3x squared. So we'll replace u prime with 3x squared. Our final solution is the sine of x to the 6th, and then multiply the sine by 3x squared. Why is that? Because u equals x cubed means that u squared is the same as x cubed squared, which is x to the 3 times 2. That's x to the 6. That's where that x to the 6th came from. Okay, now this is kind of crazy, and you'll have to think about it. We should really do another one like this that involves a composite function. We'll dig up another one.